Yeah, welcome back. I think with all those subjects that we have covered up to today, chapter 1, we have seen what is the whole subject is all about, spacecraft dynamics control. Chapter 2, I'm very sure all of you have seen through the lecture. We have covered, or rather we have revised a bit on space mechanics. And more importantly, once space mechanics is done, chapter 3 is going to look into specifically for spacecraft dynamics and control. And a field, that is mentioned here is kinematics. Now, kinematics, why we see kinematics is very important in spacecraft dynamics control, because we deal with motion, especially rotational motion, and we have multiple coordinate systems to work with, and we need to look at practically the rotational motion of the spacecraft, and we have to express it in a different coordinate system, so that we can actually know how much the system has really sort of deviated from the actual nominal attitudes. So now, first, I think let's look at the first spot where we are going to see a nutshell of all those coordinate systems that we have. If you can see in space mechanics, I think you have also been exposed to celestial coordinate system. This is actually based on vernal equinox. If you can look back, your space mechanics is very well defined. And then we have Earth fixed. That means it is practically coordinate system IJK. It is earthbound system. Well, if you're going to Mars, then actually you can have another IJK system based on Mars-bound coordinate system. Then there is two which is not been mentioned in space mechanics, is roll, pitch, yaw, or RPY coordinate system. This is new. And another one is that body fixed coordinate system. Now, when we see there are four important coordinate systems here actually that we are going to use throughout this course. What we will start is that to make sure we understand that we need to actually have all these coordinate systems, a reason being our spacecraft is indeed flying or orbiting around the planet Earth. So that means you already have one coordinate system that you need to define, at least, either celestial or Earth fixed. Now, in for space mechanics, we have seen that what are the differences, and we have transformation, basically transformation matrix that we have used to transform the coordinate system from one coordinate system to another coordinate system that we have seen. For spacecraft dynamics control, what we want to do is that we can combine these two coordinate systems into one, and we call it celestial Earth fixed coordinate system, which means that you can still see the vernal equinox system. So when you see a vernal equinox, you know practically that's how we start defining the design on orbit. Or rather, if you have 6 orbital criterion, you want to design an orbit in space, we will start in basically celestial coordinate system, where we pick vernal equinox basically as the first reference point. Then from there we start defining the orbit, or we start designing the orbit based on all the 6 orbital elements. Now, having said that, we extend that. We say that, okay, fine, why not I combine this both and I call it Earth fixed, as long as I know that my X axis is coincide with the actual vernal equinox, then it is practically for me a Earth fixed coordinate system. So throughout this semester, we are going to talk about only 3 coordinate systems, which is going to be again and again appear. Celestial, or rather inertial. This is also can be mentioned as inertial, celestial, inertial, Earth fixed coordinate system. So this is actually one, and then that means you can imagine this coordinate system is already somewhere in starting from planet Earth. So you have one coordinate system already. Second coordinate system that we want to talk about is practically RPY. The local, to be precise, is a local vertical, local horizontal system, which has the pitch, which has the roll, which has the yaw. Roll towards the flight direction, pitch is basically normal to the particular orbit, and your is actually towards to your nadir. That means towards to your planet Earth. Inverse of nadir is basically zenith. That means you're looking into the sky. So this is very well. Coordinate system is defined. So when you look at spacecraft dynamics control, we have two coordinate systems already here. One is inertial Earth fixed, combination of both into here. Okay. Then you have second coordinate system specifically for the orbit is local vertical, local horizontal, and this is basically is new for you because this is going to actually give us the actual, I would say, sense of the motion of the spacecraft from here, as you can see. So when you define this particular coordinate system, you have practically three axes, roll your pitch, and you have three rotation along the axis side. So you have a pitch rotation, you have a roll rotation, and you have a yaw rotation. I think you have seen this convention in aircraft as well. This is a very similar, only the direction is slightly different compared to what we use. Then another important coordinate system that we want to bring in is that spacecraft that we are going to fly. Now if you're going to put in a satellite, or you are going to actually fly the space shuttle, you need to have the rigid body into here. So which means that I bring this rigid body and I put it inside here. I'm going to have now three coordinate system. Earth fixed. I have local vertical, local horizontal, roll yaw, RTY, roll pitch yaw, and then I have a body coordinate system. Your spacecraft fixed coordinate system is a body coordinate system. And more often than not, we see that this body coordinate system is basically parallel to the principal axis of the satellite. That means X, Y, Z of the body is what you are seeing here as spacecraft fixed coordinate system. Okay, let's go on, move on to next page. We will, when looking at all those coordinate systems that you have seen, so I've given a quick, I would say, overview. More importantly, remember inertial or celestial is basically Earth. The Earth is center, and we are going to pick this. And you have seen that actually it starts from first day of Aries point. That means it's vernal equinox is there at x-axis for us. Important, please do mark this. This is important. Second, Earth fixed, which I've explained just now. Although it is a Greenwich meridian at x. In our case, it's vernal equinox. That's why I say we have combined this both for our convenience. So this is very important. Then we have already one coordinate system. Then we have a spacecraft fixed. Spacecraft fixed is indeed your body coordinate system of the rigid body. If you have a space satellite, so you have X, Y, Z. If you have a space shuttle, you also will have a X, Y, Z. And then you have RPY. This is an orbit. Basically, in orbit, you have another coordinate system which is called RPY, and RPY is also, we mention it as a local vertical, local horizontal system. As you can see, the pitch is actually at the horizontal. That means the normal to the orbit plane. So important to remember, inertial Earth, it's one group, and you have a body coordinate system, or rather the spacecraft fixed, and you have RPY, which is just like in your aircraft. The body aircraft also do have that body system. Right, go on. All right, what we are going to see here is that I would say an operator called a direct cosine matrix. Now, why this is very important in spacecraft dynamics control? Because as I've said, you have already three coordinate systems, and assume that the spacecraft is moving towards to, let's say, if the spacecraft is tumbling, or rather, spacecraft has the rotational motion in its body system. Now, what are you going to do? You need to actually also measure how much actually has moved. Okay? So for that, we must understand that there should be some sort of operator which tells us or allows us to express this motion. So the first one, direct cosine matrix, I think you have used this also from, I think, for aircraft. It is basically, as I defined, E1, E2, E3. Okay, you have fixed. Assume this. This is very easy. Assume 1, 2, 3 is a fixed. Then UVW is basically body. Example. So now what you want to see is that how much is that the body, or rather the rigid body, has actually moved, or rather rotated, with respect to a fixed 1, 2, 3 coordinate system, or IJK coordinate system, Earth-centric coordinate system. And unit vectors are there, u, v, w. So what are we going to do is that we are going to see that how much that u, v, w has, well, rotated with respect to a fixed coordinate system. This is very simple. Each one of those components, when we write, so if I write here, for example, the actual direct cosine matrix, if I write 1, 2, 3, with respect to basically, with respect to 1, 2, 3, how much basically u, v, w has, well, rotated. That's what it means there. So here it says that, okay, it's simple, u1, u2, u3, v1, v2, v3, w1, w2, w3. And what is, these are all basically angles. How are we going to find angle? It's nothing but it is a cosine of that angle between these two coordinate system. So basically you can imagine, if you want to get an angle, you imagine you have a triangle. Okay, you have a triangle. Triangle of what? Triangle basically between the E1 and U1, for example. You have that, then you can actually use a trigonometry function. You can find the actual angle. Once the angle is found, you can plug it here. This will be your direct cosine matrix. And having this direct cosine matrix is very easy for you to do the transformation. That means if you have a current coordinate, you want to express this coordinate into a into a 1, 2, 3 coordinate. That means your reference coordinate is very, very easy. So once you have this, you don't have to do this operation. What you do is practically you will have a new set of UVW. Then you should be able to find what is basically in 1, 2, 3. Well, I would say coordinate system. So it is just basically an operator for us to find how to express my UVW spacecraft with respect to a fixed coordinate system, which is 1, 2, 3, which is Earth fixed, IJK, right? Go on. All right. So what is the beauty? Now let me mention this. As we have already have the coordinate, okay, the direct cosine matrix. Now direct cosine matrix is quite, I would say, unique because it's orthogonal. What do you mean by orthogonal? So orthogonal, if you have a matrix A, you transpose it, then you should get identity matrix. So that means that it's actually you can rotate this matrix. You can rotate. A rotation can actually take place. And attention, well, if a matrix is what is that? Orthogonal, the determinant, you should know what is the determinant like. Can it be 0? Can it be 1? Can it be -1? So in this case, if it's orthogonal, it can't actually be 0. It has to give you at least 1 or 50. So these are basic operators that we know. Now, having said that, this is quite clear. Assume that you have a UVW, you inverse that is equivalent to inverse of 1, 2, 3. That means that if you have a matrix, let's say, based on you express through 1, 2, 3, you inverse it, you should get basically a matrix that you express in a different the other coordinate system. So it's a vice versa, and you transpose them, and it's going to be transpose them to 1, 2, 3 UVW. So this is quite standard. I think you have learned in math as well. All right, now let us actually read this carefully, or rather, let us go through this carefully. Transformation vectors. Now, reference, I have 1, 2, 3. What can be 1, 2, 3? 1, 2, 3 can be our Earth fixed. I have body, UVW. Body keeps on moving with a rigid body. So what I do, I want to find now, well, what is my, new UVW, for example. When I have all 1, 2, 3, I have DCM, that means the direct cosine matrix, practically 3 by 3 matrix times 3 by 1, I should be able to get my new 3 by 1 matrix. So this is what it means. This is what it means. So if you transpose again, if you transpose that, you will actually get a 3 by 1. So this is practically, it's very convenient for us to do. That means we can switch from one coordinate system to another coordinate system by just looking or having the DCM, that means direct cosine matrix. You establish that 3 by 3 matrix, you should be able to actually move from a coordinate system, a coordinate from a coordinate system to another coordinate system with the new coordinates. That's what it means. Huh? Alright? So, okay, successive rotations. Again, please do this. Okay. As you can see, this is so convenient. Huh? Now, assume basically I'm going to rotate 1 to 2. Let's say 3 coordinate systems are there, 1 to 2 and 2 to 3. Okay? So you have 3 coordinates, 1 coordinate, 2 and third. Let's say you rotate, that means 2 rotations you do. How we can write? So the end product, this is again 3 by 1 matrix. 3 by 1 is actually a rotation, basically 3, in fact this is 3 by 3. 3 by 3 basically DCM is equivalent to 2 by 3 DCM. That means what? The rotation between 2 to 3, that DCM times basically 1 to 2. So 3 by 3, 3 by 3, you should get also 3 by 3. And if you use this, you should be actually able to get also, you want to find new coordinate, you times that, you should be able to get a new 3 by 1 matrix. Again, this is 3 by 3. 3 by 3, this is actually 3 by 1. Just like this operator. This is a simple operation. What I did is that this simple operation, I did multiple folds. Okay, that's all it is. Okay, go on. Alright, another way we can do this is through Euler angles. This I think all of you are quite familiar with. 3 sets of matrices are there. As you can see, x component involved, that means the rotation in x, rotation in y, rotation in z. Now, this is a very particular case whereby the rotation angle R basically, phi, is same basically for all the consecutive rotation. Now, in typically you can also have a different angle. You can rotate this particular axis in a different angle. That means phi 1 can be, here can be phi 2, here can be phi 3, it doesn't matter. As long as you know which axis you're rotating. Okay? So it's just like x you're rotating, let's say x, z and y, x you're rotating, so 2 should change. So 2 will change finally. Okay? So these are the typical Euler angle rotations. It's easy to be done. Consecutive rotations. I think this is you guys have also gone through this. Go on. All right. Now, for our application, we use a 3-2-1 rotation in that sense. It is z. You start with z. You start with then after that y and then x. So it is, you pick the yaw first, then you do a pitch and you do a roll. So this is quite typical convention that we do. And you can have, when you do the rotation, practically you should have the actual 3 by 3 again, a total matrix that you can write. That means the whole sets of matrix can fit into a one, the whole 3 matrix that you have seen, you can put it into basically one huge matrix of 3 by 3 by doing this operation. Go on. Alright. Third is, I think this you may not be very familiar. Call it a Euler parameter. Now Euler parameter, what it defines? Defines any finite rotation of a rigid body can be represented by rotation through a defined angle. Now, this is something for our convenience. Now, just now we were looking at 3 different angles, which means that we have roll your pitch angles for us to start rotating. Now, what exactly that we want to try to do is that why not we have another basically fourth axis. We call it basically an Euler axis E. And if I assume that I have a rotation angle, I will practically end up rotating all those 3 axes simultaneously. That's what it means. That means you have one axis. They are not orthogonal. This axis is not orthogonal. The other 3 basically are orthogonal. So you have one axis and you start actually applying an angle to rotate. Another 3 will rotate. just like this. 3 will actually rotate simultaneously. So technically speaking, I can do that. So my operator, I don't have to do a consecutive rotations just like what I've done in Euler angle. So it's much easier for me in that sense. Okay, let's see. And there is also a very particular reason why we are actually choosing this. Later we will discuss a bit more. There is a reason why this is actually becomes interesting. As it is working with maybe 3 dimension, with 3 coordinate systems, you have already practically 9 axes to work with. And I'm here coming and telling you there is another axis, I'm adding another 10th axis. But there is a huge advantage of using quaternions. Huh? So 3 independence. So this whole theorem is actually converging to a subject called quaternion, basically an operator called quaternion. So you have the 3 independent parameters is because basically their magnitude would be 1. Huh? Go on. Now, representation of this basically angle, Euler angle and Euler axis by a 4th dimensional vector is called quaternion. This is for convenience, okay? It's a hypercomplex number. So how am I going to define this? Very simple. I have E being defined, okay, as quaternion axis, and then I have the angle which I have used basically to rotate all the 3 axes. Therefore, here comes in all with the sign, and then Q1, Q2, Q3 is a function of sign basically, and Q4 is actually its cos angle. So you will have 4 components. So if I do in a matrix form, Q1, Q2, Q3, Q4 transpose is practically a new sets of parameters which can be used for us to express the actual rotational motion of a rigid body, and which can allow us also to use it for our transformation. That means what we want to transform from one coordinate system to another coordinate system that can be done with this operator. Okay, go on. Now this is something that important that we have covered. DCM we have covered. Okay. Euler single Euler axis we have covered. Okay, it's very easy, very clear. Okay, very clear, very easy to do. We have Euler quaternion. We have just covered the quaternion. Okay, I will explain GIP methods. But GIP is actually, unless you want to really do orbital mechanics on studies of perturbations, etc., then analytical studies actually quite convenient to use GIP's method. Then you have our Euler angle. Now, direct cosine matrix is interesting. Reason being, there is not much of actually, we won't encounter much on singularity. Now, reason being, remember, for us we had 3 basically principal axis, I, J, K, or 1, 2, 3, and you have U, V, W. Now, what we did basically to find an angle, there is only one cos function that actually we used to find the angle between these 2 vectors. That is E1 with respect to U1. That's what we said. But we didn't do anything else. So it is quite easy basically for us to find one coordinate, or rather one value of the angle by just using the direction cosine matrix. So therefore, you can avoid singularity. No trigonometric function. Now, what do you mean by singularity? Singularity happens when you hit numbers like maybe like tangent, for example. When you do, there is no, it doesn't converge. It doesn't converge to a value. It gives you an infinite. So when that happens, tangent, normally we have that problems. So when we have that, so we can't be actually using this quite often, especially for a higher numbers of higher angle. A small angle, fine. You can be safe with the DCM. You know, it's no problem. You can be very safe with DCM. But slightly on a higher, about 90 degrees, then it becomes a bit more complicated. Okay. Now, single axis is clear, but then there's only one redundant parameters. It is normally we in spatial dynamics control, we can actually do, we can use it just to do one task. That means I want to move x axis, I want to rotate x axis maybe 30 or 40 degrees or even 50 or 60 degrees. I do it just like that, just only one axis. But if I want to simultaneously control all the three axes, this becomes inconvenient because you're only talking about one single axis. We need three axes established, like DCM and quaternion. Now quaternion is again very convenient. Reason being, no singularities, just like before here, no singularities, no trigonometry functions as well. And you will see there's no cos, there's no tangent, I would say, to start with. The most time the deadlock will just starts actually when you start working with tangent, and for a larger angles. And here we have one parameter. So normally we use quaternion, is very convenient for attitude determination or attitude estimation. We can use quaternion. Even for attitude control, we can actually use quaternion. You will see more and more of this. Euler angles obviously is very important. We will obviously use for 3-axis control. Why Euler angles? Well, because it's quite convenient for us, but problem is that it is only valid for a very small angle. That means you're not talking about huge angles, not about like 90 degrees and all that. It's quite dangerous because you go into a deadlock, actually the singularity happens. So small angles, and if you look at our attitude, most of it is basically very small angles, 1 degree, 2 degree, 0.5, 0.001. So it's quite convenient to use. Remember, and there's also, if you look at all those derivations that we have, that we are going to actually have a look at it, most of it basically we have also used Euler equations basically to develop those, well, I would say governing equations. And if you look at that and coupling with the Euler angles, it becomes much more practical, much more easier for us to use. It's easier. And plus, we know that we can operate only in a very small angle. That is what we need to look at. But if you're looking at a very large angle, then quaternion is the safest. We can do any slew. Let's say you want to do slew maneuvers, huge, multiple slew maneuvers. You can even think of actually looking at doing a quaternion. So it depends on the actual application. But for our course, we say that okay, 3-axis attitude control, we will actually stick with Euler angles, and we will look at all our equations later will be also based on this. But on the other hand, we will also carefully use quaternion as well for our conveniences. And don't forget, DCM also will be involved in some derivations. So 3 important items will be there, 3 important operators will be there. Alright, let's look at the quaternion. Now, quaternion describes the attitude B, that means attitude B with respect to frame A. It's just like the DCN as well. So I'm going to now express basically with respect to A, I am actually looking at B. So there's D painting, this is IJK, Earth center, and this is actually your rigid body or your spacecraft. So it's simple. Okay. Now, if you look at attitude, the description of that rotation around Euler, let's say this is the definition that we have given just now. Euler angle is phi, and I can rewrite conveniently as before, and you have seen this before as well. So this is the same. Not much change. It's just that remember, don't get lost with the actual reference. Reference can be IJK or Earth-centric. B can be your spacecraft. Okay, it can be between any 2 coordinate systems. No problem, you can use it. But for an example, I've given you so that it's easier for you to understand. Okay, now if both are parallel, these are some of the important items you have to remember when you use quaternion. When both are parallel, that means that both coordinate systems are parallel. That means x, y, z, or I, j, k, and let's say this u, v, w are exactly parallel. Then Q4 will be 1. So when Q4 is 1, you know basically both coordinate systems are parallel. Don't have to do any transformation because they are all together. They are in a plane. You don't have to do any rotation to express it. They are parallel. So whatever you express, is equivalent to expressing in both planes. So important, you check. So which means also when Q4 is not equivalent to 1, Q4 not equivalent to 1, that means they are not parallel. Practically, you need to do that operation. That means you need to do a transformation to express the coordinate system. Okay, I give 2 cases in this case. Assume if they are not parallel, basically they are not zero, I can actually find the Euler axis, and I can also find the actual value of the what is that theta, okay, the phi, sorry, the phi. You can actually find the phi. Now the interesting part is this: assume that if it's zero, so technically I'm going to actually apply this. So you want my Euler axis, I can actually have Q1, Q2, Q3. The value should be given, and this is a signum. I think some of you may know. Signum is just a matter of this sign, either positive, negative, or zero. That means if it's a positive number, then if it's, let's say, a +1, then it is anything positive. X is bigger than 0, let's say, then it's positive number. It's equivalent to the signum value would be +1. If it's X is let's say below 0, then the signum value would be -1. And if it's 0, let's say X, say this Q1 is 0, then it should be actually 0. Now, note very, very clearly here, this is basically is just magnitude, but then when this becomes 0, what exactly you will have? You will have basically the unity, the unit. That means what? The Euler axis alone will be there. Practically, you don't have any magnitude, but you just have the Euler axis. That's what it actually means, man. Quaternion is actually 0. But if it's quaternion 4, quaternion 4 is 1, then you know that both of these axes are together. Now, more often than not, we will always work with this Q is more or less 1, we say. Because why? We are working with very, very small number of small angles. So we say that it's almost 1. That means they are almost parallel, but there is basically error. Okay, go on. Inverse quaternion. The quaternion have an operation. Inverse. If you want to inverse the quaternion, it's very simple. They will actually appear. The inverse sign will appear in Q1, Q2, Q3. Okay, it's easy. Okay, this is very important. You multiply quaternion. When you multiply quaternion, it means that you are rotating. Please understand that. You multiply quaternion. Quaternion multiply another quaternion. It means that you are doing rotation. How the rotation is like is this. This is a quaternion matrix I define. Let's say Q2, let's say prime 2, rotate prime 1. So the new would be is easy. How am I going to do the rotation? Is I build a quaternion matrix based on prime 2 as it is, okay, prime 1, sorry, as it is. Then I can actually express my Q2. So this is actually 4 by 1, this is 4 by 4. So you would have 4 by 1 quaternion. Okay? So what exactly it means that it is a multiplier, a rotation. It actually is a rotation. So this is basically is a we call it a quaternion matrix for which allow you to rotate clearly. So you want to rotate this. So you want to rotate, let's say, from one well, I would say one axis, one coordinate system to another coordinate system with respect to what? Let's say, then this will actually take the quaternion. Yeah, it's 4 by 4. We will do an exercise for you to understand this clearly, the application part of it. Go on. Alright, successive rotation. This is quite interesting. Huh? Now, if you look at it, this is the operation of quaternion, how they work. Assume that you have 4 elements, Q1, Q2, Q3, and Q4, and then you want to express from what frame A, one frame to another frame, and then from this frame to this frame. That's what you want to do. Okay? See how easy this we can do. Now, A to B, basically quaternion AB. Easy. BC, quaternion BC. Now look at the operation. B to C is basically its inverse. C to B is also inverse, okay, of CBC. And likewise, AC is also inverse. More importantly, so they are very, very compatible, very, very easy to use the operator. Now, AC, this one, I define this as quaternion AB multiply quaternion BC. So operator just now we have known. So we need to build a transformation, or rather a quaternion matrix 4 by 4. 4 by 4 will be, we use quaternion BC to build the matrix and then inject our AD quaternion. So you will have 4 by 1. So 4 by 4, 4 by 1, new 4 by 1 quaternion you will have. Very, very easy. Transformation from B to C. Okay. B to C. Look how convenient. Inverse A, B, and AC. Correct? Yes, you can get that. So how can I rewrite this? I can rewrite this. It's easy. I have a 4 by 4 quaternion matrix. AC quaternion. That means 4 by 4 I have. Then I rearrange it. Can you go before, please? It means that you have still 4 by 1 matrix. You rearrange it to 4 by 4. That means what? You plug all those Q1, Q2, Q3, Q4. You plug inside so that you get 4 by 4 quaternion matrix. That's all it is. Go on. So it's likewise AC. Plug into that. You build 4 by 4 quaternion matrix. Likewise, transformation A and B is also similar. So this X, what exactly happens is that it is, although you multiply, you actually is rotating. You are rotating it, rotating that into BC. So, for example, here AC. So this is basically AC. So you want to actually look at this to this. Okay, how to express that? Then you do 2 consecutive rotation. Then you should be able to have that transformation matrix. Okay, simple operation again. This is the one. Again, rotation 1, rotation 2, quaternion 1, quaternion 2. You can have 2 operations here. Rotation, practically you have a rotation, you can do the rotation, or you can actually you can pass by the quaternion. So what exactly happens here? Sequence 1, rotation 1, rotation 2. Quaternion, what I do? I just multiply the quaternion. So when I multiply the quaternion, I should have basically the new quaternion matrix, this one. This will be what? Quaternion which is from here to here. That means what? 2 rotation, after 2 rotation. Okay? And then for transformation matrix, this is also the same. Don't forget, here we have 3 by 3. Here is 3 by 3 transformation matrix. Here basically 4 by 1, 4 by 1, 4 by 1. But in order for us to do this transformation, we need to plug in the Q into 4 by 4 matrix. Then you can get this thing done. Quaternion transformation matrix is this the one. See? Okay, but don't forget 3 by 3. This transformation is 3 by 3, yeah? Okay, good. Okay, quaternion deviation. This is very important. Again, please to understand that, give you a scenario. Now, let's say I have a frame. Let's say this frame is basically IJK, earth centered. Then assume that this is my body frame, or rather, I would say, you know, body. You can take body frame, and this is, you can say, practically deviation. Okay, a deviation. Okay. Now, or let us give you a good scenario. Let us say this is actually IJK. Let us assume that this is basically the orbit frame, in orbit frame, and let's say this is the actual body frame. Okay. Always to understand that when we want to measure any deviation in spacecraft, it has to be in a body frame. It will be measured in body frame. Okay, your sensors, all your sensors that you embark, just like in aircraft, it will be measuring in a body frame. Now, what exactly happens? Now, let's say I want to actually look at my orbit frame. And my orbit frame says that there's a quaternion. Let's say I define the actual transformation or reference is actually Q prime. But what exactly happens? It doesn't actually give me Q prime. It gives me Q double prime, which means that it's already there's a deviation, and this is a deviation. If very good, no issue, this will be here. That means perfect, ideal, no disturbance, nothing, everything is fine. This will be here. There won't be any deviation. There won't be any, you need not calculate any quaternion deviation. So which means that when you are flying, you have a Earth-centered IJK, you have local vertical, local horizontal system, everything just perfect. In fact, your body coordinate and your local vertical, local horizontal system also all together. That means if you look at the quaternion, Q4 is 1. Q4 is 1. So they are all together. So when they are all together, there is no issue. But more often than not, it's not like that. It's always like, I would prefer he to be perfect. Let's say this is our local, we can write this. This can be a local vertical, local horizontal. Example, this is your IJK, your Earth fixed, inertial Earth fixed coordinate system coming from planet Earth fixed. And this is actually your body. Let's say the spacecraft, which has a deviation, and there is a sensor in the spacecraft which measures this. Now, what can I need to know what is the deviation, right? If I know the deviation, then I can correct it. Let's say I have already moved. How to know? I have already moved, let's say 1 degree. I have already rotated 1 degree along yaw or roll or pitch. I need to know, so gyro will tell me. Gyro say, hey, you already rotated 1 degree along roll. There is already a deviation, there should be a deviation. So this deviation is very easy basically for us to calculate in using quaternion. You see, it's sort of convenient. All we have to know, the actual Q prime 2. What is Q prime 2? Q prime 2 is inertial body. That means your body attitude. That means your body quaternion, current measured body quaternion by the gyro with respect to a fixed inertial. That you must know. That can be if you have a sensor, you should know that. You plug it into here. This is what is supposed to be desired, right? So you check what is your local vertical, local horizontal quaternion. Plug it into here, you will get the exact deviation. Means the deviation that you need to correct exactly. You don't have to calculate, you just have to correct this deviation. Once you correct this deviation, your fixed IJK, initial fix, is just like what we planned with respect to your local vertical, local horizontal coordinate system. Because the body has been moving, it already has a deviation. If it doesn't move, it's here, it's perfect. Perfect. Okay? Can we go on the, okay? Right. DCM. Now, DCM computation. If you have quaternion, can I compute direct cosine matrix? Can. Well, you have a quaternion, Q1, Q2, Q3, Q4, plug it inside here, you will have already a DCM. When you have a DCM, you should be able to actually do transformation. Okay, let us see. I'm using now I have quaternion. What I do? I build a DCM, that means a direct cosine matrix. I should be able to do a transformation as well. Okay, let's see. In this case, F1, F2. Coordinate system 1, coordinate system 2. And I have Q1, 2. That means what? This quaternion is what I've already built here. Okay, now what exactly I want to know is that, look at, I want to express F2. I want to know here, I want to express here, what is the V in coordinate frame 2 with respect to coordinate frame 1. I've already have Q12, which is this. Okay, so that means that if you have a quaternion of F2 with respect to F1, I can build a direct cosine matrix. I can direct cosine matrix 3 by 3. I can use it if I want to now find what is my new coordinate. Yeah? In my coordinate system, what is my actually new angle or attitude given the old coordinate readings, which is this. Okay, so when you update this, this will be can calculate. So I do not have to know the coordinate system here. I can actually operate without even the coordinate system when I have this matrix. When I build a matrix, I already know I can operate it. So basically, I don't have to do anything. I just actually use this new update. New update. If a new angle comes in here, then I'll update this new. So practically, the coordinate system you don't see anymore. That is actually the operation of DCM. You see how quaternion can be helpful and how DCM can be helpful. We will do an exercise so that it will be much clearer in this transformation. Go on. Okay, this is very important. Change of sign of all quaternions basically doesn't affect the DCM. So it's fine. You change, DCM remains. It's very convenient. It's very, very convenient in the sense. Okay, change of sign here doesn't affect. So your DCM that you build is actually you can use it. Now this is I have mentioned to you. Euler angles for small rotation in basically our attitude works, attitude control works. We assume that it is almost one, almost parallel. You see, very small. This is not exactly one, but almost there, 0.9 sometimes. Then when that happens, you have roll, you have pitch, you have yaw, and you should be able to know your is equivalent to. So if you have a value, so half of the pitch angle is equivalent to the actual value of the quaternion angle. Okay, rotation. So it is very n is in radian per second. Okay, this is easy. So you can calculate your basically your roll, pitch, yaw. If you have a quaternion, you should be able to calculate. If I give you Q1, Q2, Q3, Q4, let's say 1, Q1 is 4, and I give you value, you should be able to calculate the value of roll, yaw, and pitch easily. Go on. Okay, now let us see quaternion in RPY. Now we have learned that in space mechanics we have 6 orbital Keplerian. Now in this 6 orbital Keplerian, we say that good. How are we going to actually express this orbital Keplerian in my local vertical, local horizontal system? Now that can be done easily. Remember, this is actually given in your space mechanics. So what I do is that, look, for inertial, I have three types of rotation I want to do. In order for me to, what I'm going to do here is simple. I look at the my coordinate system. I look at the 6 orbital element. I know I am in IJK, but it is a very special case because I've already combined, remember, the initial, I call it initial Caesarian plus initial fixed or other earth fixed. Combine them both, we will see afterwards. I've already have a coordinate system. In this coordinate system, I define the 6 orbital elements. Once I have the 6 orbital element, what I'm going to do is that I'm going to make sure this 6 orbital element, it is going to come back to my local vertical, local horizontal system. That's what I want to do. How am I going to do this? I have to keep on actually rotating the axes so that they can actually come together parallelly. Just like that. Let's see. What I'm going to do, I'm going to rotate this here. Then let's say this is here. Okay, then I'm going to rotate this axis. and so on. This is what I'm going to do. Then so that they are going to actually be parallel. So once they are parallel, I can express them in even quaternion if I want. Again, look at this, is important. 3, 1, 3, 3, 1. It means that sequence of rotation. Sequence of rotation, 3 means is basically your Z axis. So your Z axis, huh? Your Z axis, your roll axis, Z, Z, and roll. Okay? This is a sequence of rotation. So first, let's see. And this, you use this angle. This angle is all basically available in your space mechanics. Okay, I'll give you one example so that you can actually respond. Okay, how can I actually write this? It's easy. First of all, you look at it. Now, this is actually initial fixed Earth coordinate system. That means what? Celestial, initial, and Earth fixed is already been together, and my vernal equinox is here. It's bingo. Mean to say, I have respected how I have been building or designing an orbit in space. I start with celestial, and this is how I have. And now I have added my local vertical, local horizontal system. So the first rotation is actually looking at my Z. Okay. Yeah. Sorry, my Z here. Okay. First is actually looking at Z. So my Z, and I'm going to use my right extension. Right. So what I do, I hold my Z. I move to just like my right extension. I move. That's what you want, bro. Go back before. That's what EAS is do. I hold 3. That means I hold Z. Then I move this much, and this is my right extension. So let me go. I hold. I move. What exactly I've done? Remember, vernal equinox is defined in equatorial plane. When you hold the Z and you start actually moving up, you are practically bringing it from equatorial plane to the orbital plane already. You're already done. You already reached the orbital plane. So this is already you're at the orbital plane. In your orbital plane, all you have to do is that you make sure all these 3 axes back to just like X, Y, Z. That means what? You see here, this has to, this Z must be same. This is your Y. So everything has to come back to the sequence of rotation is that. So you do second. Let's see. The second is basically your before please. Yeah. So I've performed this already. Now I have my X. What the instruction is that? Inclination. Okay. Let's see. Where's my inclination? Okay, I'm already here. Then I have to actually rotate my X, right? So I rotate my X so that my inclination will be up, back to the from orbital plane, the actual plane, the orbit plane. That means the inclination is already, you already have I. Once you have I, you just follow through that omega, argument parity, then the true anomaly, you will end up already here. End up here, you perform plus minus 90 degrees, that means plus and minus 90 degrees, you already swap the coordinate system to be exactly like LVAH now will be exactly the same pattern of initial coordinate system. That's right. So once that is done, when you do that kind of a sequence, so this, we can write this operator as a quaternion. So quaternion of initial with respect to local vertical, local horizontal is that. So when I'm here flying on local vertical, local horizontal orbit, I should be, you give me 6 orbital element, I should be actually be telling you what is my local quaternion based on my orbital element. It's a very simple operation. Okay, we'll try an exercise of this also. Go on. Okay, now this is very important. How we have also talked about the deviation just now. Okay, now the attitude deviation. Why quaternion becomes so easy? Because no trigonometric function here. Do you see any trigonometric function here? No. What I can do, if I already have this quaternion matrix, I can practically keep on updating Look, this is the equation. Huh? The deviation of the quaternion that I have with respect to time. That means the derivatives of the quaternion itself. This I do update every time. A new quaternion, a new quaternion, a new quaternion, new. New means where? New means is your body. You have a new body, then I find the quaternion. You move this way, then I have a new quaternion. I update. I find the deviation. This is the same. Can you go back to the before this, please? Before. Yes. New. Find the deviation. Correctly. Then you're already here. Then no. It is well, you see, still nothing happened. All 0, 0, 0, 0, 1. Nothing happened. But then the value, there is already different. I need to know the deviation. I need to update. I need to know the deviation. I have to update. So for this operation, how this is done? Go back to that. This is what I'm talking about. Update this. New, you'll give me new. But look at this, you've got to be very careful of this. Now, angular rate need to be actually also be included inside this equation, because your update is fine, but there are actually angular rate which involves not only basically the current orbit, and not only current coordinate system, but the initial system also. So here, the omega, which this you're going to plug this 4 by 4. So look at the matrix. Half 4 by 4 matrix times by 4 by 1 matrix. You should get the Q quaternion deviation 4 by 1. This is what you should get. But be careful, very, very careful on this. This is extremely, extremely tricky here. 4 by 4. When you already found this 3 by 1, this is 3 by 1. This is 3 by 1 matrix. When you find this 3 by 1, then it's no problem. You can put it, you can rearrange them into 4 by 4. But before finding, you must actually really understand this. Now, this, okay, if you look at it, orientation of frame B against frame A. Now, frame B, assume this frame B is basically your local vertical, local horizontal. Okay, say frame, sorry, of your body actually, your body. Now, so frame B is body against frame A. Okay. Now, this transformation matrix, A would be your local vertical, local horizontal. Okay. Then you have what is the actual deviation, not deviation, but actual angular rate of the local vertical, local horizontal itself. Remember, local vertical, local horizontal, they have 3 attitude, roll your pitch, and they have a rate of roll, rate of yaw, and rate of pitch as well. This is the one. So make sure you write this clearly. This is actually local vertical, local horizontal. This is basically with the body, local vertical, local horizontal with respect to the body. That means I am looking at the body now here. And this inertial is basically at body. That means from inertial, that means Earth, I have a sensor, and sensor gives me with respect to the inertial with respect to body. So I am already in a body here. This is a body. This operation is already in a body. Body and body, you will get the actual angular rate. Take this, plug into here. Okay. Now the quaternion deviation you will find actually in the body. When you find the quaternion deviation in the body, you should be able to correct by using the control system easily. You already know what command to actually use. So remember this. This is body. Sensor gives you this. The gyro will tell you this. You put a gyro in a spacecraft. Gyro will tell you this with respect to inertial reference. Inertial to the body. This is basically your current local vertical, local horizontal. What is that? How is there any rate? I'll tell you. And this is basically the actual transformation of this with respect to the B. That means the body itself. So all of them are in the body. You take them, plug them here. This is, if you look at it, 3 by 3, 3 by 1, 3 by 1 matrix, 3 by 1 matrix, 3 by 1 matrix. Take 3 by 1 matrix, build 4 by 4 matrix. Reason being, the size of our quaternion is 4 by 1. So there will be basically, alright? Any questions in that sense? Okay, are you doing a rotation here? Are you doing a rotation here? You are not actually doing a rotation, you are just doing an update. This is not a rotation here. Why is it not a rotation? The axes are all not in play. If axes are in play, let's say 1, 1, 1, say not 3, 3 axes, 1, 1, 1, probably you're doing rotation. Identity, orthogonal, remember. But then no, here you are not doing rotation. You are doing updates basically. So when you do updates, that's what actually you have. Alright? We go on. This is a simple thing. What I'm going to explain to you here is IJK system, XYZ, and you have basically 1, 2, 3 system. What are you going to do is you are finding the actual new DCM. Okay, for example, let's take that this example, I and B. If you have this is just a repetition, I and B. Let's say you want to find the angular acceleration, angular rate of B. Okay, you have DCM, I of B, and you have basically the rate of here. Okay, so you will have practically 3 by 3, 3 by 1, 3 by 1. Same goes for all the other sweep method. This is just a sort of a quick look of how DCM works. Very fast you can actually with the DCM, and without doing much of transformation in that sense. Okay, I think that's about it on Cartesian coordinate. Anything else?